Alright guys, another video here. Whoops, I forgot to write the title up there. We're going to be talking about gas laws today. Woo! Alright, Tiny Tim's here. He loves gas laws. That's a lie, he doesn't. It's pretty much all math, and Tiny Tim hates math. Okay, so you know there's the ideal gas law, which is PV equals nRT. There's the combined gas law. But we're not really going to go into those. Those are fairly basic, simple. I mean, the only trick with PivNerd is to make sure your R values are the same. The combined gas law must be in Kelvin. The temperature has to be in Kelvin. But those are pretty simple gas laws. I mean, we introduce those in regular chemistry, honors chemistry. We're going to do kind of a more deeper understanding of gas laws and how gases interact and react. Okay, so there's the molar volume of gas at STP. The molar volume of gas at STP says that 22.4 liters equals 1 mole. It's the molar volume. Molar volume. Volume of a mole. Okay, so what that means that at the same pressure, the same temperature, equal volumes will have equal moles. Right? Let's say I didn't have 22.4. Let's say I had 11.2 liters. Well, that's obviously half a mole. Or let's say I had 44.8 liters. Well, that's 2 moles. So equal volumes of a gas, and it doesn't matter what the gas is, as long as it has the same conditions. It doesn't even have to be STP. As long as the gases have the same conditions, the equal volumes are equal moles. Okay, now that's an important concept. It's a very important concept. And it leads to things like Dalton's law of partial pressures, and PivNerd and the combined gas law, and all of those. Okay. The way, let's say, the way to increase the moles, point there, bullet point there, let's say to increase moles, let's say I'm still keeping the constant volume, I have to increase my pressure, meaning pack more gas into the same volume of space, or increase my volume. I'm sorry. I said constant volume, I meant constant temperature. So to increase my moles, I can either increase the pressure by packing in more gas, not by increasing the temperature, because that would obviously just make them move faster. But I could increase the pressure by packing in more gas, or I could increase the volume, right? Thereby putting more gas in it, right? I'm not saying you take a 1 liter container of gas, and if you increase it to 2, I have more gas in there. Picture this more like a balloon. All right, a 1 liter balloon has less gas than a 2 liter balloon, right? Because the volume increases. All right, so in both cases, you are adding more gas. You're either adding more gas to change the pressure. Let's say it's a rigid container, I'm adding more gas to change the pressure. Or it's a flexible container like a balloon, and I'm adding more gas to increase the volume. In either case, I am adding more gas. That's why I'm increasing moles. Okay. So, let's talk about Dalton's law of partial pressures. So Dalton's law of partial pressure is deceptively simple, yet very difficult at the same time because of the implications of it. Dalton's law of partial pressure says that the pressure of container 1 plus the pressure of container 2 plus the pressure of container 3 equals my total pressure. All right, now that may seem like a very simple concept, but we can also think of it in terms of moles, right? Because let's say all of my volumes and temperatures are the same, then it would also affect the moles of a gas. All right, I'm just, pulling something up here. Okay. Now, it's important to realize at this point that pressure, I don't know if there's anything, pressure is my collisions with the container. Okay? So pressure is literally just collisions with the container. It's the gas particles colliding with the walls of the container. So to increase pressure, I can either put more gas particles in there, so it's colliding with the walls of the container more, or I could heat the gas up, and it's colliding with the container more and harder. because the particles are moving faster at a higher temperature. All right, so those are the two ways that I can change the pressure, kind of the two easiest ways, I guess I should say, that I can change the pressure. Okay, so let's do kind of a sample problem with Dalton's law. And I'm kind of pulling it off my laptop, which is why I'm looking contemplatively off to the side. You know, it's kind of like the model pose here. I'm trying to pull it up here. Probably should have thought this. Okay, so let's say I have 3 containers. Let me grab a different color because I'm not really liking this blue. The red seems to pop pretty well. Let's say I have, see what, it does pop pretty well. Let's say I have 3 containers. The first container has 2 atmospheres of a gas in it. These are all 1 liter containers, by the way, and it's argon. The second container is also 1 liter, like I said, and we'll pretend that it's neon. Okay. The third container of a gas, we'll say, is also 1 liter, sorry. And we'll say that it's helium, sorry, not hydrogen, helium. And let's say, so we have 3 containers. I'm sorry, we have 3 containers. We have argon, neon, and helium. I'm telling you what the atmospheres in the first one are, and I'm not telling you the other 2, because I'm evil and mean. And we say that you take all 3 containers and you put them together. You put them into what's called a previously evacuated container. So a container with no gas. So I put them into a container of gas, and we'll make it 2 liters just for fun of this mixture. And I want to know what the pressure in the final container is. Well, obviously you can't do it yet, right? Because you only know 1 pressure. I know that's going to be more than 2 atmospheres, but I don't know how much more. So I tell you that the ratio is 2 to 1 to 6. Okay? So it's a 2 to 1 to 6 ratio. Take a moment, pause the video, try and calculate it. See what you think. Okay. Hopefully you'd pause the video and calculated it, or hopefully you are doing it now, or had just done it, or will do it in a second. Okay. I'll assume at that point everyone has, if you're willing to. So I have a 2 to 1 to 6 ratio. Well, hopefully you realize that that's 2 atmospheres to 1 atmosphere to 6 atmospheres, right? Sorry, sig figs. A 2 to 1 to 6 ratio. Good. Well, so if I were to use Dalton's law of partial pressure, P1 plus P2 plus P3 must equal my P total. Well, great. So 2 plus 1 plus 6 is 9. Here's the trick. 9's wrong. 9 is not the correct answer. If this were a 1 liter container, it would be 9 atmospheres. Right? If this were a 1 liter container, I would have 9.0 atmospheres. Right? But it's not a 1 liter container, right? It's a 2 liter container. So I take my 9 atmospheres, my pressure, if I double the volume, what happens to my pressure? If I double the volume, going from 1 to 2, what happens with my pressure? Hopefully at this point you are either know exactly what happens, or you know maybe let's plug it into the combined gas law and see. Turns out if I double my volume, I cut my pressure in half. The answer is 4.5 ATMs, 4.5 atmospheres. I double my volume, I cut my pressure in half. Okay? It's an indirect relationship. Okay, last but not least, we have one last thing I want to talk about with gas laws. It's fast, I promise. I know you all have really important things to do, and you're probably watching this at like 2 in the morning because you guys are crazy over-involved, but I'm not judging, not judging. All right, the last thing we need to talk about is diffusion. That's a gas spreading out. There's a much more technical definition, but we don't care. It's a gas spreading out. It's like the reason why in these bathrooms, when the kids spray a can of Axe spray, you don't smell it just in the bathroom, you smell it all the way down the hall, right? Because of diffusion. The gases diffuse. Okay? That's why in your 3rd period class, when that girl sprays a bottle of perfume on herself, you smell it everywhere in that classroom. Because the gases diffuse. They spread out. It turns out This is based, or the speed of diffusion is based on your mass. Right? Heavy particles don't move or diffuse as quickly as smaller particles. Because while the gas particles may have the same kinetic energy, the same temperature, we all know that it takes more energy for a big thing to move, right? It takes more energy for a Mack truck to move down the road than a tiny little smart car. Because it's bigger. Right? So even though they have the same kinetic energy or average kinetic energy, it just takes one to move, it takes the bigger one more energy to move faster. So the smaller smart car, it will zoom down the road at a much higher speed than the Mack truck if given the same amount of energy or the same horsepower. That's why Mack trucks have a tremendous amount of horsepower and smart cars have like 2. Right? Because big things, it takes big things a lot of energy to move quickly. So if I have big particles, like let's say, wow, I really wish I could think of one. Let's say sulfur hexafluoride. Sulfur hexafluoride is a very heavy particle. It will not diffuse nearly as well as helium. This will diffuse slowly. This will diffuse quickly. Okay? This one diffuses faster because it's lighter. If they have the same amount of energy, this one will move faster than this one. This one's slower. Right? This one is Tiny Tim. This one is me. Right? It takes Tiny Tim a lot less energy to run a mile than it would take me to lumber through it. Right? It would probably take Tiny Tim a lot less time. I don't know. We've never run the mile together. It's not the kind of thing we do. Alright, so it would take me longer because I'm bigger and heavier and I require more energy. So it takes SF6 longer. The experiment they do with this is they grab a glass tube. So they grab a glass tube. Kind of like your udiometer tube, but it's open on both sides. Glass tube. And these glass tubes are several feet long. The longer, the more accurate the experiment. Right? And they take a cotton ball and they soak it in a liquid, a volatile liquid. Let's say this cotton ball is soaked in HCl. All right? And they take another cotton ball and they soak it in something different. So let's say cotton ball, and it's soaked in, oh, I don't know, HBr. Okay? That's a horrible example. I mean, RbOH. Okay? So, we take a look at these two gases. Now, what's going to happen, obviously, is these two gases are going to start diffusing down the tube, right? HCl is going to diffuse. Rubidium hydroxide is going to diffuse. Okay? And where they meet, there's going to be a reaction, because one's an acid, one's a base, and we'll be able to see where they meet. That's why HBr was a bad choice, because it won't react with HCl, because they're both acids. Okay, so they're going to diffuse. Where do you think these two are going to meet? Where do you think these two are going to meet? Pause the video. Do you think they're going to meet in spot 1? Do you think they're going to meet in spot 2 or spot 3? All right, pause the video, take a guess. Okay, spot 1 is clearly closer to HCl. Spot 2 is, we'll call it the middle. Spot 3 is closer to RbOH. Now we said that light things diffuse faster. Well, HCl is much lighter than RbOH. So HCl is going to diffuse faster. So in the same amount of time, it's going to diffuse much farther than the heavier RbOH, which has to lumber to get there to react. Okay? The lighter one diffuses farther. Okay, I said it was quick. I hope I meant it. This hopefully wasn't too long of a video. It was very colorful at the very least, a little Christmassy. I love it. Hopefully this helps you out with gas laws. Thank you very much.